Picture trying to run an empire before numbers were invented. You have thousands of sheep, bushels of grain, and tax collections pouring in, and you need a way to track all of it. Early on, administrators tried scratching a single line into clay for every individual item. But when you hit 100, let alone 10,000, that endless row of identical marks becomes visually unreadable and mathematically useless. The sheer volume of raw information overwhelmed the human brain. Bureaucrats were drowning in data points, unable to process the wealth their empires generated. To keep these massive societies from collapsing, they needed to condense raw tallies into a usable format. They needed data compression. Around 3000 BCE, administrators in ancient Egypt figured out how to make that leap. They shifted the entire underlying logic of how we quantify reality. Instead of logging items one by one, they started packaging them into defined groups of 10. This established what mathematicians call a landmark number, a specific threshold where you stop counting individual things, bundle them together, and represent them with a completely new visual symbol. We can see this system actively used in surviving written records from the era, showing how mathematics evolved from moving physical pebbles into a highly structured accounting system. By packaging data into these distinct landmarks, the Egyptians turned counting from a chaotic physical chore into a sleek, abstract system. This chart maps the first 3 landmarks: a single staff for 1, a heel bone for 10, and a coiled rope for 100. The mechanical threshold is strict. Gather 10 of one symbol, and you trade it in for the next symbol up. To write down a massive number, you no longer had to draw thousands of separate lines. You just stacked a few of these specific landmark groupings next to each other. Because every tier scales up by a multiple of 10, we call this logic a base 10 or decimal system. The modern arithmetic we use today operates on this exact same engine. It is an inherited 5-millennium-old habit, born from the biological coincidence that humans happen to have 10 fingers. Let's run a thought experiment. Imagine having to rebuild all of mathematics from scratch, assuming humans only grouped things by 5 instead of 10. In this system, landmarks are powers of 5, 1, 5, 25, and 125, represented by a triangle, square, hexagon, and circle. To build 143, we extract one circle for 125, leaving 18. That remainder becomes 3 squares and 3 triangles. Changing the base completely alters the visual language on the page, but it preserves the flawless underlying logic of mathematics. These visual base systems turn complex addition into a mechanical process that works without any memorization. Look at this Egyptian addition problem. The action is straightforward. Dump all identical symbols from both numbers into one massive pile. Then apply the carry-over mechanic. When a pile hits 10 identical shapes, erase them and draw the next landmark shape. Multiplication utilizes this same sliding logic, merely shifting a symbol up to its next power tier. Ancient arithmetic operated as a physical, visual game, a process of trading shapes based on a few unbreakable rules. This logic, swapping many low-tier units for one high-tier unit, leads directly to modern computing. By shrinking the base down to 2, we get binary, where every piece of data is bundled into groupings of 1s and 0s. We can view numbers as a form of human-designed software, a specific logic used to categorize reality. By mastering these mechanics, we gain the ability to invent entirely functional mathematical universes of our own. Mathematical literacy begins with the architecture of the group, the universal rules of how we bundle and scale the world around us.